Okay, welcome to part 2, oscillators, or give me the beat, boys. This time we're talking about making systems that create sound with a distinct pitch. There's not a lot of preamble to this, so let's go straight to the clipboard. Okay, to put it perhaps over simply, sounds with a pitch have one big property: repetition. Well, repetition that's fast enough and not too fast, and it actually has to change from time to time. If you think about it, just silence is pretty repetitive, but it doesn't have a pitch. However, if what we have is a changing wave that repeats between 20 and 20,000 times per second, those actual endpoints are pretty fuzzy and things get blurry and messy once you get near them. At the low end, pitch starts changing to rhythm, and at the high end, we just stop hearing things at all. But the vast majority of all musical notes or interesting pitch sounds are well within those bounds. And the wave doesn't have to repeat 100% perfectly. There's a lot of interesting subtlety in that fact that we can get into, but for now, we're going to focus on simple repeating waves. So let's introduce some concepts. The systems we're creating here can be viewed as having two sets of corresponding properties. What I'm going to call the auditory properties, which are the ones we hear, and then what I'm going to call the physical properties, which are the properties of the waveform itself that we can draw on the piece of paper. So for our auditory properties, we're going to deal with the following: loudness, pitch, and timbre. Now, it's spelled like it should be timber, but it's actually, for complicated etymological reasons, pronounced timbre, or if you're being super fancy, timbre. I don't care how you pronounce it, and I mess it up all the time, but I'm going to generally try and stick to timbre. And what it refers to is sort of the quality of sound that isn't loudness or pitch. So, for example, you could play a piano and a guitar at the same note and the same loudness, but they sound different. And that difference is the timbre. It's kind of a vague term. So these three auditory properties correspond really closely, but not perfectly, to three physical properties of the waveform. So the first one is the amplitude. Which is the difference in magnitude between the highest and lowest points in the wave. So the highest and the lowest point on the wave. So inside our computer, that would be the sample value, or outside our computer, that would be the air pressure. Either way, the bigger the difference, the louder it sounds. Well, our perceived loudness isn't 100% based on the amplitude, but it's so close that people will often use the terms interchangeably. It's also important to note that we're talking about the relative distance between the top and the bottom of the wave. So, for example, this and another wave that was like this up in the air with the same relative amount, I guess you have to imagine that one's twice as big, would sound just as loud. You can forget about that guy for now. Just worry about this guy. Okay, so next up, pitch corresponds to the frequency or the period of the wave. They're interchangeable concepts, but we'll talk about frequency more, so I'll leave it at that. Now, the frequency is how many times, well, the period is the amount of time between each cycle of the wave, so how long it takes for the wave to go from the start to where it repeats. And the frequency is how many times it does that within a second, or some other length of time, like a year or a minute, but it's pretty much always a second. So just assume that any frequency mentioned is talking about within a second, unless you're told otherwise. For the most part, we talk about frequency instead of period, unless we're specifically talking about one cycle. Now, the frequency doesn't exactly 100% correspond to the pitch. There's some special cases where we can fool our ears, but it's so close that, once again, the terms are used sometimes interchangeably. And the unit of frequency is the hertz, which basically means the per second. That is to say, if something happens 100 times in a second, it's a frequency of 100 hertz. And usually the thing that's happening per second is gathered from context. So like with one of our oscillators, it's wave cycles per second. Or if we're talking about hogs crossing a road 5 times every second, 5 hertz would mean 5 hogs per second. You just use the context. And so now we'll talk about the timbre. Timbre corresponds to the shape of the waveform. That is to say, something like this versus something like although I guess our frequencies are different, but this shape of the wave, how this one's just going up and down, this one's ramping. And this one has the loosest correspondence between the auditory and the physical. It's also the hardest to describe directly. Like, I can't really tell you what timbre something will have just by looking at the wave shape, other than sort of the more jagged and jumpy something is, the more bright or buzzy it will sound. It's really not. That's not even a perfect thing. And as you'll notice from me struggling to talk about it, our vocabulary, in English at least, for talking about timbre is really poor. So the best way to gain intuition about how shape and timbre correspond is to listen to stuff. But also, this has a great advantage, because this lack of obvious correspondence is a great place for you to get creative. So with pitch and amplitude, you can just sort of dial it up or down, but with timbre, you can go crazy. You can make all kinds of different shapes. You could imagine something like that, or all sorts of neat stuff. Okay, so when we finally make our oscillators, we'll be controlling this frequency, this amplitude, and this shape to get our sounds. But there's one more concept I want to talk about, which is phase. And what phase does is it describes the position within one cycle of the wave. So I'll draw a new cycle down here. Real top quality drawings. So phase is a number which represents how far along we are in the cycle. For example, we can, be at this point, which point our value is here, or, at this point in the cycle, which one our value is down here. So we can talk about the value of a particular wave shape at a given phase, or sometimes we can think about a phase as like an offset value. So for example, this cycle, we could redraw it, but starting at a different point. So like that. Believe it or not, to our ears, those would sound exactly the same. And those are ways we can think about phase. As to the actual numbers we'll use, there's 2 common ways of going about it. One way of doing it is thinking of our cycle as a circle, and your phase increases as you go around the circle. So this would be 0, degrees of phase. Down here would be 180 degrees. Over here, 270. Back up into 360, and 360 and 0 are the same. You'll commonly, I guess if you're into math, you could, call it pi radians. But this kind of way of talking about phase is used a lot in regular conversation. You'll hear a lot about things being 180 degrees out of phase. But another way of thinking about it is thinking of your phase as starting at 0 and going until all the way done. And all the way done you can just represent as 1. And this has a really nice advantage because we can just scale this into whatever range is convenient for thinking about our shape. So for example, we might notice this shape has 2 distinct parts. So when we think about the shape, we might think about drawing from 0 to 1 and from 1 to 2 and know the difference. But we can always scale a phase of 0 to 1 into that. So now let's think about how our actual program is going to look. So if you recall, our job is to fill up buffers with samples, and that means we need to figure out 2 things to do to draw a wave. We need to ask, what phase are we at? On this sample, and what value is our wave at that phase? And if we can answer those 2 questions for every sample, we're done. Just pop that value into the sample. So if we think about an oscillator as starting at phase 0 and ticking over to 1, then for each sample, we start at phase 0, then for each sample, we'll just say each of these lines is the sample. We go along some amount and pick up some amount of phase, and then we go along some more and pick up some amount of phase. We can just figure out how much phase we need to pick up each sample to get us all the way there. And then each sample, we add the amount of phase we need to increment into we add the amount of phase we need to pick up into where we already were. And we check to see if we've gone all the way around. If we have, we wrap around back to the start. And then we just figure out our wave's value at that point. So this technique of piling up the phase at each sample is called phase accumulation, because each step you accumulate some more phase. It's not the only way to make a digital oscillator, but it's a really simple and versatile way. It's also really, really flexible, and it's used all over the place. In order to implement it, there's basically only one more thing we need to figure out, which is how much phase to accumulate every sample. So to do that, we need to know 2 things: what frequency we want and how fast the samples are coming. So that second value, the rate at which the samples are coming, is called the sample rate. Nice and intuitive. It's pretty much always expressed as a frequency, and it's typically, for audio systems, a value like 44,100 samples per second, or 44,100 hertz. We'll write that down. Here's some other ones. 48,000 is also relatively common. On really high-end systems, you might see 96,000. You rarely see it go any lower than this on any real audio system. So typically in a computer software, or typically in a computer audio system, you can either ask the hardware what sample rate it's running at, or you can tell it what you want it to run at when you start it up. In our example programs, we'll ask the machine what sample rate it's using, but sometimes in other languages and other libraries, it goes the other way around. You tell it. So now that we have this sample rate and we know what frequency, we can pick what frequency we want, we need to figure out how much to accumulate. And this is where it gets really handy to express our phase as a value between 0 and 1. So basically we want to go frequency cycles per second. We know frequency cycles per second. We know that we have our samples coming at sample rate, abbreviated SR, samples per second. So if we just divide frequency by sample rate, we will get cycles per second over samples per second. The per seconds will cancel out, and we will get how many cycles per sample. And that will be our increment value. That's what we accumulate. Given that a lot of pitches in music correspond to frequencies in a range of like 30 to 4,000 hertz, this is probably going to be a pretty small number. So yeah, let's review our program a little bit. We'll write some pseudocode over here. Basically, we need to hold the phase that it's at. We'll call these variables. Our current phase, which we initialize to 0. We'll need to figure out an increment, which we get by dividing our desired frequency over the sample rate. And if we want to change it, we can just change the frequency and figure it out again. It's good to leave this thing as a variable you can change. And then we will need a function which goes from a phase to a value to output. This guy is what we call in the business the fun part. This is where you really get to be creativity. This is where you really get to use your creativity. Since I can't tell you what a wave shape will sound like, you can just play around with stuff. But for synth enthusiasts and as a place to start, I'll mention 4 classic wave shapes that you see a lot. Here's the classics. We have the sine wave, which corresponds to the trigonometry sine function. So, a sine of theta between 0 and 2 pi or 360 degrees. We've got a square wave, which I sort of drew earlier. It goes from maximum to negative maximum, back up to maximum, back down to negative maximum. So there's its cycle. You may notice that this is the namesake of the channel. We've then got the triangle wave, which is the example wave I've been drawing up here. It ramps up to maximum, then ramps down to negative maximum, then ramps back up to 0. And finally, we've got the sawtooth wave, which starts out and ramps all the way up and then jumps back down. So that would be one cycle right there. And you could also think of the sawtooth as ramping down. It doesn't really matter. So these waveforms are really common in synthesizers for various reasons, mostly historical, and because waveforms like this can be kind of easy to make with discrete electronics. But we live in a computer world, and we can make any crazy waveform our heart desires. So check out in the example page where I'll have these and some other fun waveforms to play around with. And one last little note. This oscillator technique is really flexible. So for example, we could set the frequency to something way lower than we could hear, like say 0.25 hertz, like 1/4 of a hertz, meaning one wave every 4 seconds. And there's also not any kind of law saying we have to use an oscillator's output as a sample value. You could, for example, have an oscillator that outputs values from 0 to 1 and multiply its output by the output of another oscillator to get sort of a tremolo volume going up and down kind of effect. Or you could do any other manner of creative things. I'm going to have a bonus example page showing a fun musical example of how to get clever with this technique. And that's all. So far we've made a lot of systems that just kind of drone on forever, but real things in the real world or real musical instruments tend to make individual sonic gestures that sort of change over time. They have a start and an end. So next time we're going to talk about envelopes and basically have the final set of simple techniques we need to make full-fledged quote-unquote instruments. See you then.